Today we're going to start looking at lesson 2.6, which is called Combinations of Functions and Composite Functions. Our objectives today are we are going to find the domain of a function, and we are going to combine functions using the algebra of functions, specifically finding our domain with that. Sorry, my pen doesn't seem to want to cooperate. All right, so the domain of a function. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. We will exclude from a function's domain real numbers that cause division by 0 and real numbers that result in a square root of a negative number. Okay, so essentially, we're not going to be looking at a picture anymore and saying, okay, from this graph, let's identify the domain. Sometimes we're just going to be looking at the function itself. So if we're looking at an equation, we are going to determine what the domain is. And like it says, anytime we have a variable in our denominator, we just never want to divide by 0. So we never want that denominator to turn to 0. And anytime we have a square root, we never want to be dealing with imaginary numbers because we're talking domain in a set of real numbers. So we'd have to take that into consideration as well. All right, so let's find the domain of each of these functions. We've got f of x equals x squared plus 3x minus 17. Let's start there. It's important to kind of understand what kind of function we are dealing with. Because this is an x squared term, well, we hopefully are getting very familiar with what kind of functions we have based off of the parent function. So x squared, remember, is a quadratic. It's the shape of a U. Okay? Remember, when you're dealing with quadratics, you can think about creating a table of values. You can square negative numbers. You can square 0. You can square positive numbers, and every time you square those numbers, you are going to get a real number. So because that's the case, we would then be able to say that our domain is essentially the set of all real numbers. And so that means that I can plug in any negative number, I can square it, get a real number. I can plug in 0, square it, get a real number. I can plug in a positive number, square it, and get a real number. So as far as defining our domain as interval notation, it's going to go from negative infinity to positive infinity. Okay, if we look at this second function, we've got g of x equals 5x all over x squared minus 49. The fact that I see that I've got division here, I need to focus on the denominator for a second, because like the last slide just said, we never want to divide by a number and divide by 0. That's just not something that we want to do because that would be undefined. So we want to be figuring out what values are going to turn my denominator to 0. Well, in order to do that, we can set our denominator equal to 0 and we can solve for x. So there's technically two ways to do this. I could factor, because x squared minus 49 is a difference of two squares, or because I just have x squared and a number, I can do the square root method. So if I do the square root method, I'm adding the 49 over. When I take the square root, that tells me that I have two answers. So 7 and negative 7 would be those numbers that x cannot be, because the moment I plug those into my denominator, I'm not going to be getting a real number. I'm dividing by 0, that's undefined, right? That's the only restriction that I have in this particular function. So when I'm dividing, I just don't want the numbers that turn my denominator to 0. So as far as writing our domain, that means that I can have any negative number going until negative 7. But remember, I don't want to include negative 7. So here's the first part of my interval. So negative infinity to negative 7, not including negative 7. Okay, but that's not the only part that I can plug into x and then get real numbers. So on the right side, I can go to the right of negative 7 up until positive 7, but I also cannot include that number. So anything between -7 and +7 are going to be numbers that fit in my domain. But we're still not done. I then can keep going to the right of 7 up until positive infinity. So we've got 3 different sets of intervals here. We've got the union symbol in between them to represent the fact that I can put all of those sets together, and all of those numbers combined give me my domain except for -7 and +7. Okay, if I look at this last function here, I see f of x equals the square root of 9x minus 27. Remember, I never want to have a negative number underneath my square root. So what I'm going to do in this case is what I have underneath the radical, it can equal 0 because I can take the square root of 0, or it can equal a positive number. So I'm going to take 9x minus 27 and set it greater than or equal to 0. I'm going to solve for x, and that will end up then being my domain. So that means that we're going to add 27 over to the other side. By adding 27, it does not change the inequality sign. Then I'm going to divide both sides by 9, and when you divide by a positive, it once again does not change that inequality. So 27 divided by 9 is 3, so x is greater than or equal to 3, meaning I can plug 3 in, I can get 0, I can take the square root of 0. I can plug in 4, I'll get a number that's positive, I can take the square root of a positive number. So because I know that x has to be greater than or equal to 3, I can write this now as a interval. I can include 3, so that's my bracket, but that's the smallest number, and I can head up towards positive infinity. So 3 with the bracket, infinity would be then my domain. So pause the video, see if you can figure out this domain. F of x equals 3x divided by the square root of x minus 4. All right, we have 2 situations here. We have a fraction, which means I never want my denominator to turn to 0. And we also have a square root, which means I never want to have a negative number under the square root. So normally if I have the square root, just like that last problem we did, we would take what was under the square root and we would set it greater than or equal to 0. But remember, because the square root's in my denominator, I don't want it to equal 0, and that's why I had to use the inequality sign of just greater than. So x minus 4 is greater than 0, and then I moved the 4 over. So if x is greater than 4, that's why there are no brackets. I go from 4, which is not included, up to infinity. All right. So the algebra of functions. So we're talking the sum, the difference, the product, the quotient. So adding, subtracting, multiplying, dividing. So it says let f and g be 2 functions. The sum, f plus g, the difference, f minus g, the product, f times g, and the quotient, f divided by g, are functions whose domains are the set of all real numbers common to the domains of f and g, defined as follows. When we are looking at, so we'll see something on the left-hand side like this in our textbook. So we will have in parentheses f plus g, and then we'll have an x in parentheses next to it. It's essentially just telling us that we're adding f of x plus g of x. When we see something like f minus g in parentheses, and then that parentheses with the x next to it, that just means that we're taking f of x minus g of x. Notice that in both of these, f are first, and that's why the f of x function is going first. Had it said g plus f in parentheses, then it would have been g of x plus f of x. So just follow the letters and put them in the correct order. If I have f times g in parentheses, that means that I want f of x times g of x. So notice that there's no symbol in between the f and the g, so that means multiplication. And then the quotient is f divided by g in parentheses. So because f is on the top, we want f of x divided by g of x. But remember, g of x cannot equal 0 because I don't want to divide by 0. Okay, so when it said that its domain is all real numbers common to the domains of f and g, so notice how there's that intersection. So it's only what they have in common. I'm not putting everything together. It's just what they have in common. All right, so let's take a look. We've got f of x equals x minus 5. We have g of x equals x squared minus 1. We're going to do the operations that are provided to us here. We'll get an answer for the operation, but then we're also going to determine the domain. So f of x plus g of x is essentially what this first one is saying. So I want to take f of x plus g of x. Well, f of x is defined as x minus 5, plus g of x is defined as x squared minus 1. I just need to combine like terms. I want to go in standard form as well. So I want the biggest exponent first. X squared is the biggest, and I don't see anything to combine with that. Then there's an x. I don't see anything to combine with that. Then I've got some numbers. -5 minus 1 is -6. This is my new function when I added the f of x and the g of x together. Okay, so now I want to determine the domain. Well, if I'm looking at what these functions have in common, the fact that the f of x function, this is a line because it has a degree 1. The g of x function, that's a parabola because it's a squared term. But if I'm looking at both of those, there's no restrictions on the domain. I can plug a negative, a positive, and a 0 in and form a line. I can plug in a negative, a 0, or a positive and square it and still get a real number. So because both of these don't have any restrictions, if I look at my new added function together, it's also a quadratic, which means that doesn't have any restrictions either. So it's just like that very first problem that we did. Our domain is going to go from negative infinity to positive infinity. There's no restrictions on what x can't be in either the f of x or the g of x, and now in its combined function as well. Okay, if I look at this next one, since it says f minus g, I know I want to take f of x minus g of x. So once again, f of x is x minus 5 minus, and now in parentheses, there's two things for g of x. So I have to keep them in the parentheses so I make sure that I actually subtract correctly. So I'm going to have to distribute that negative. We'll have x minus 5 minus x squared plus 1. Just now, like the addition problem, I can start combining like terms. I want to put it in standard form, so the x squared term goes first, but there's a negative with it. The x is still positive. There was nothing to combine with that. Now I have -5 plus 1, which will give me -4. So here is my function. Just like before, f of x is a line, g of x is a quadratic. There is no restriction on either one of those. My newly formed difference is also a quadratic. So similar to then the domain in the first problem, we are going to be going from negative infinity to positive infinity. There's no restrictions on what I can plug in for x in either of my original equations or in my newly subtracted equation. Okay, we're using the same functions, and now I want to find the product and the quotient, and once again determine the domain. So remember, this is like f of x times g of x here. So we've got x minus 5 times x squared minus 1. I'm going to distribute this out. X times x squared is x to the third. X times -1 is -1x. -5 times x squared is -5x squared. -5 times -1 is +5. I don't see anything to combine. I am going to rearrange the terms to put it in descending order, or what we call standard form. And so x cubed minus 5x squared minus x plus 5 is going to be the product. So once again, we're dealing with a line that doesn't have any restrictions. We're dealing with a quadratic, which doesn't have any restrictions. This new product has a cube. So think about a cubic function. I can cube a negative number and get a real number. I can cube 0 and get a real number. I can cube a positive number and get a real number. So once again, there's no restrictions here. My domain is going to go from negative infinity to positive infinity. Okay, in this next one, we are dividing. Since the f is on the top, we're thinking f of x divided by g of x, because the g is on the bottom. So f of x, we've got x minus 5 on the top. G of x, we've got x squared minus 1. So once again, no restrictions on the f or on the g. However, this time, because we're dividing, when we see that there is a denominator, remember, I can never divide by 0. So this time we actually are going to have some restrictions. So I have to look at the denominator, and I never want it to turn to 0. So since it's x squared minus 1, set it equal to 0. We can start solving for x. That tells us what is going to be excluded from our domain. So once again, this is factorable because it's a difference of squares, but I can just do the square root property here. I'm going to add the 1. I'm going to take the square roots. When I take the square root, I get 2 answers. So x cannot equal 1 or negative 1. But basically, then any other number in my domain is going to work. So when we write out this domain, we can go from negative infinity up until negative 1, but negative 1 cannot be included because that turns our denominator 0. But we're not done. We can go to the right of negative 1 up until positive 1, but once again, we cannot include positive 1 because that would turn our denominator 0. But we're still not done because now I can go to the right of 1, and then I can move up and I can hit any other positive number. So this whole entire expression right here would be my domain. Okay, let's do the same thing, but let's look at a different function. Let's look at f of x equaling the square root of x minus 3. And we've got g of x equaling the square root of x plus 1. So let's add, subtract, we'll also multiply and divide. So if I know that I want to take f of x plus g of x, we've got the square root of x minus 3 plus, and then I've got the square root of x plus 1. Now, in order to actually add, we have to have the same thing underneath the radicals. X minus 3 is different than x plus 3. So these are not like terms. That's all I can do as far as showing what my addition is. So I'm done there. Now we have to start talking about the domain. Because we have a square root, we are going to have restrictions. If I look at this first radical, what I have underneath, remember, you would take the x minus 3, and it can equal 0, or it can be any positive number. So that means if I move the 3 over, my restrictions here is that x has to be greater than or equal to 3. If I look at the second thing underneath this radical, I would set that greater than or equal to 0. So subtract the 1 over, and x has to be greater than or equal to negative 1. So both of these have restrictions, which means that I want to find what they have in common, because essentially that's the two different terms that I have with the addition. So I need to find where do they start overlapping. Okay, so you can think about it like we did in the first half of chapter 2. Okay, I could go from negative 1, 0, 1, 2, 3, 4, 5. Okay, so if I think about 3, it can be including 3 or anything greater. If I think about negative 1, it can include it or be anything greater, but I want the intersection. So I want where are they overlapping? Well, notice that they overlap starting at 3. And so that is going to be my domain. 3 can be a number that goes underneath both those radicals, and I get a real number, and then anything positive from there. So this would be my domain. If I am subtracting, we'll do the f of x minus the g of x. So once again, f of x is this square root of x minus 3 minus, and then the g of x is the square root of x plus 1. Once again, because those terms underneath the square roots are not the same, I cannot combine them any further, so this would just be my subtraction. And then our domain is the same idea. We've got restrictions for both. Because my difference is essentially both of those together, I just want the commonality or the overlap of the domains. So same thing. It would start at 3, and it could go up to positive infinity. know. These things are not going away. Okay, so hopefully it'll go away when I start writing. So notice that we have the product. So I want to take f of x times g of x. Not quite sure why this isn't going away. So let me do this. Okay. All right, sorry about that. So we want f of x times g of x. So we're going to take the square roots of x minus 3 times the square root of x plus 1. Now, if you remember with multiplication, when they are both underneath a radical and they are, in this case, both a square root, that means that I get to make it one big radical, and then I actually get to multiply those terms that are underneath together. So we can actually multiply those two binomials. It just has to stay underneath the radical. So if we start, well, you know what? I'm okay. Let's just leave it like this. Because that's going to help us out when we have to determine our domain. So let's just leave it like that. And then as far as our domain, remember with the first one, we have to have x being greater than or equal to 3. With our second one, x has to be greater than or equal to -1. If I look what I have underneath that square root, once again, the first number that would work is when I have 0. And so because we're dealing with the product, we need to pick numbers that are going to then turn our denominator, or not denominator, but what's underneath 0. So in this case, we are going to want once again the intersection of where those two overlap. So it's still going to be that 3 is the first number that works for both of these, because originally the g of x I can't say, or sorry, for the f of x I couldn't plug in -1 because I'd have a negative number underneath. So even though -1 works in the product because it would turn to 0 there, it doesn't work originally in the f of x. So it's just like all our other domains at this point. We are going to keep it with 3 being included up to positive infinity. All right, let's talk about division. So we want f of x to be on the top and the g of x to be on the bottom. We are dealing with the square roots of x minus 3 on the top divided by, then we have the square root of x plus 1 on the bottom. Because division, when we have a square root on the top as well as the bottom, we can write it as one big radical. So we'll have x minus 3 divided by x plus 1 all underneath the square root. So this is my quotient. So now let's talk about the domain. Notice how, once again, we do have one big radical. So I know that I can only have positive numbers, and it has to fit the intersection of what my original ones are. So that means that we have to have at least 3 be the starting point. Now that works out for us because if I look at the denominator, I am going to be able to plug 3 in, and it's not going to turn that denominator to 0. And if I start plugging in any positive numbers greater than 3, it won't turn my denominator 0 either. So I did have to make sure that my denominator wouldn't turn to 0, and with it starting at 3, it wouldn't. So just like all of our other ones, it does work out where we can start with 3 being included, and we can go up to all of our positive numbers. All right, let's take a look at one more set of functions here. We've got f of x equals x plus 2 all over x squared minus 9. And we've got g of x equals 3x minus 1 all over x squared minus 9. So when we are adding the f of x plus the g of x. The nice thing about this is that we are dealing with fractions, but it looks like our denominators are the same. So that's going to help us out greatly. When the denominators are the same, that means that we get to keep the denominator as it is, and I get to start combining all of the terms in the numerator. Well, x and 3x are going to turn into 4x, and then 2 plus -1 is going to give us a positive 1. So this will end up being the sum. And now we have to talk about the domain. Because we are dealing with a fraction, I have to look at the denominator, and I never want my denominator to turn to 0. Well, the nice thing about all three of these functions are that all of the denominators are the same. So once I've determined which numbers don't work for one of the fractions, those are the numbers that aren't going to work for all of the fractions. So remember, I'm taking my denominator, x squared minus 9. I'm setting it equal to 0. Those are the numbers I cannot have. So this is technically a factorable polynomial, but it's also, we are able to solve using the square root method. So I'm going to add the 9, and then when I take the square root of both sides, we get two answers. We get 3 and negative 3. So those are the values that I can never have in my domain because they'll turn my denominator to 0. So that means that any other negative number is going to work. So I can go from negative infinity up to negative 3, but I cannot include negative 3. Then I can go to the right of negative 3 up to positive 3, but I cannot include that one. And then I can keep going to the right of positive 3 all the way up to positive infinity. So here is the domain. Same idea then when I am subtracting. The nice thing about this is that we have the same denominator. So we want x plus 2 over x squared minus 9 minus 3x minus 1 over x squared minus 9. So we'll keep our denominator the same. But now when we are doing subtraction, make sure that we understand that I am subtracting the whole entire second numerator. So I am going to have to distribute the negative to both the 3x and to the negative 1. So that would give us x plus 2 minus 3x plus 1 in the numerator. So when I combine those, we've got x minus 3x, which will give us a negative 2x. We've got 2 plus 1, which is going to be 3. This is all over x squared minus 9. So this would be my difference. Okay, something that I forgot to mention, but it's not going to be relevant in either one of these cases, is that technically, like I said, the x squared minus 9 is factorable. It factors into x plus 3 times x minus 3. Once we've combined our numerators, if we can take out a GCF or something like that, we would want to. But if I can factor the top, and if I see that there's something on the top that is also on the bottom, then we would want to simplify that down. In the first one, 4x plus 1, I couldn't factor that any further. So since that binomial I don't see in the denominator, I know I'm done. In the second numerator, this negative 2x plus 3, there's nothing that's in common there for me to factor, so I won't be able to simplify that down either. So that's why I know that that's my final answer. Okay, as far as our domain goes, same idea. All of our denominators are x squared minus 9, so that means 3 and negative 3 won't fit. So it's going to be the same domain. I go from negative infinity to negative 3, not including it. On the right side of negative 3, we can go up to positive 3, not including that. And then on the right side of 3, we can go all the way up to positive infinity. All right, let's look at the product and let's look at the quotient. So if we are multiplying f of x times g of x, I am going to have x plus 2 over x squared minus 9 and multiply that by 3x minus 1 all over x squared minus 9. So when you multiply fractions, you multiply straight across. So that means that the x plus 2 needs to get multiplied by the 3x minus 1. So I'm going to start distributing. X times 3x is 3x squared. You know what? I'm just going to write it before I factor this. You know what? Let's just do this. Let's just write it like this for right now. So let's write it as the x plus 2 times the 3x minus 1. And then same idea on the denominator. We've got x squared minus 9 times x squared minus 9. Okay? So technically, like I said, the denominator is factorable. That factors into x plus 3 times x minus 3, and it happens not once, but it happens twice because there's 2 of them. So I would be okay, because I do want everything as factored as possible, because then we can determine if something is going to reduce. So don't distribute. Let's just leave it like the x plus 2 times the 3x minus 1 on the top. But then here, I can write this because there's 2 of these x plus 3s. I can write it as x plus 3 quantity squared. And then the same thing with the x minus 3. I can write it as x minus 3 quantity squared. This is going to be my product. There is nothing on the top that is the same as the bottom, so I know that I'm done. Okay, as far as my domain then goes, all of the denominators are the same. Even this new denominator, it's not going to change the fact that if you plug in -3 or +3, you're going to turn your denominator to 0. So our domain is still not going to include those numbers. So we can, go from -infinity to -3, not including it, from -3 to +3, not including it, and then from 3 to +infinity. Okay, and then our final one here, we are going to divide. So we're going to have the f of x on the top and divide that by the g of x on the bottom. So that means we're going to have x plus 2 over x squared minus 9 and divide that whole thing by 3x minus 1 all over x squared minus 9. Okay, when you divide, you want to think of it as multiplying by the reciprocal. So essentially, the numerator is going to stay as it is, but the denominator is going to get flipped because I get to change division into multiplication. So I get to then put the x squared minus 9 on the top and the 3x minus 1 on the bottom. So technically, each of these we would then multiply straight across. So notice that because I have an x squared minus 9 on the top and an x squared minus 9 on the bottom, those divide out. So this leaves us then with an x plus 2 on the top and a 3x minus 1 on the bottom. Neither one of those are the same, so this would be my quotient. So this time, my denominator of my new quotient is different than the original denominators of my functions. So my original denominators of x squared minus 9, which means that 3 and -3 aren't included in the domain, is still relevant. But I also now am going to have another value that won't work. I have to set this 3x minus 1 equal to 0 and figure out that when I add the 1 over, and then when I divide by 3, I also cannot have a value of 1/3 because the moment I plug that into my denominator, I'm going to get 0. So this time my domain is just a little bit different because we have an extra number that we can't include. So we can go from -infinity to -3. We can go from -3 up until 1/3, but we can't include the 1/3. Then on the right side of 1/3, we can go up to +3. And then on the right side of 3, we can go all the way up to infinity. So this time we had a little bit more that we needed to go about in order to figure out our domain. So because our denominator was a little bit different from the original denominators, we had to look at that denominator, find the number that did not work for that domain, and include it in the overall domain. So a lot of information. I would suggest that you pause the video, try these two functions and the 4 different operations and determine the domain for each. All right, so a lot of information, but notice that the f of x function is a quadratic, g of x is a line. There's no restriction on those domains. When I added them, still had a quadratic, so that's why there was no restriction on the domain. When I subtracted, I make sure I subtracted very carefully, ended up with a quadratic, no restrictions on the domain. When I multiplied, I ended up with a cubic, still no restrictions on the domain. But when I divided, whatever was in my denominator, I never wanted it to equal 0. So set x plus 10 equal to 0, which means x cannot equal 10. That's the only number that cannot be included in my domain. So a lot of information here, but that's us finding domain of a function and starting to do our algebra problems, adding, subtracting, multiplying, dividing, and finding the domain of each of those as well.